Hi everyone, this is a bonus video for this unit. It's intended to be watched either at the beginning, like a big overview of the entire unit, or also at the end to kind of tie it all together and put it together. One thing I've noticed from this unit is that the hardest part for students is knowing how to set up the structure of the integral. So I hope this video will help to clarify a lot of these concepts and also tie them together. And don't you like Olaf? He was a project someone made. So this chapter starts with the area between curves, right? And so we talk about two curves, neither of which are an axis, and we want to find this area in between, right? So we set up an integral and we do the top curve minus the bottom curve if we're in a horizontal position. And then we have these intersection points, and so we spend a lot of time finding those intersection points, and this gives us the area of a curve. And the area of the curve is always, the area between curves is always positive because it's area. It's like total distance is always positive. It's a positive number. And when we first started doing integration, we were doing the area between the curve and the x-axis. And sometimes the area was above and sometimes the area was below. And so the areas, and I put in air quotes, were either positive or negative depending on their position in relation to the x-axis or the y-axis if you're going left and right. Because that's what negative numbers are, right? Negative numbers indicate direction. They either indicate that you are a negative number is moving the opposite away from zero than a positive number. If you have a negative angle measure, like negative 30 degrees, it's moving in the opposite direction than a positive 30 degrees. If you have a negative exponent, x to the negative 2, then this could be rewritten as 1 over x squared, right? It says that the negative indicates to us an opposite direction. So we don't want area to be negative. Area in our life is positive. It's always a positive, like time moves forward, and so distance is positive and all of that. So we used a specific method of doing top minus bottom, right? We did top minus bottom, or if we were doing dy, we did right minus left. And that would always get us a positive area. And so if you're trying to find the area between curves and you get a negative area, you did something wrong. It's backwards. Okay? So this is important to begin with because this area between the curves is going to be our base. It's always going to be our base. And from this, we're going to take this base and we're going to revolve it around an axis and make a solid. Or we're going to use this base and we're going to make a solid by putting known shapes on top of it to make a three-dimensional object. And so in order to do that, we're going to set up an integral, right? Because we're going to take all these little shapes and we're going to do an infinite number of them and we're going to add them up. But this is our base, and that's what's really important. So the first method for finding the volume of a solid is to take a known figure, this rectangle that's right here, and take this and revolve it around an axis. Well, I want you to notice here that these are all circles, right? These are disks. This is called the disk method. So the volume of a three-dimensional disk, and then we're going to have an infinite number of them. We're going to add them all up, and we're going to find the volume. So in order to do that, we use the integral, right? But these are circles. This disk is a circular figure, and the area of a circle is pi r squared. So when you go to set this up, there's a pi something squared dx. And this part in here is going to be the radius of the circle squared, pi r squared. Then we decide that not just a disk, but we might make something that looks more like a washer. Here's a washer. And a washer, you know, is just a circle with a circular hole in it. So we have two radii, right? And so when we go to set up this integral, it's going to look like a washer. So it's going to have something squared, the outer, minus the whole. So the whole disk minus the whole, they're both circles, because we could write them separately, right? So we would have pi r squared minus r squared, and this is washer. So it kind of, if you look like, it looks like a washer. So you've got the outer minus the inner. So then finally, we decide to take that base, right, that top minus bottom base, and we start putting shapes on it. And so like this one has squares, and this one has a right triangle. It kind of looks like a right isosceles triangle. This looks like a rectangle. This looks like semicircles, right? But it has the same base, the card, it's all laying on that same base. And so what we did, if you haven't watched that video, but what we did is we spent a lot of time deriving formulas for the area of these shapes with respect to them sitting to the side that's sitting on the base, right? So when we get ready to make the integral, they're all these integrals are in the same form. Remember, pi r squared minus r squared, and then like say if I wanted a square, right? The square was, the area is b squared. So this looks like dx square. If I wanted a right isosceles triangle, right, it would be the same thing. I would just put a 1/4 out there. If I needed a semicircle, pi over 8, we spend time deriving those. And equilateral triangle. Well, how do these all look alike? Disk, washer, and they all start to look alike by its shape. So then if you're on an AP problem and they say, we have a rectangle that is the square root of blah, 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 like I derived in there, then you just set it up. So it would be, right? Or whatever it is that the area of that shape is. If it's a known cross-section, or it's a disk, or it's a washer, disks and washer uses circles, pi r squared. And these others, they don't use, you can see why they wouldn't have pi in them unless they were like a semicircle, and the semicircle would have pi over 8. So I wanted you to see how these are all related to each other. That area of the base, we find the area of the base, and then we work with disks, and then we work with washers, because disks and washers are an awful lot alike. And then we use cross sections, which means shapes of any kind. They don't have to be disks. And so I hope this has been helpful. And I hope that you have watched all of the other videos that kind of develop this bit by bit, but this is just more of an overview. I hope it helps, and I hope to see you in class.